Okay, so in this lesson, we are going to go through Pascal's triangle and the binomial theorem or the binomial expansion. However, starting with Pascal's triangle. Now, Pascal's triangle is in fact used to determine the coefficients of the terms in the expansion a plus b to the n. So if we look at the different rows of Pascal's triangle, each corresponding for a value of n, of course here where n is a natural number. So when n is equals to 0, a plus b to the 0, anything to the power of 0 is just 1. Now when n is equals to 1, a plus b to the 1 is in fact a plus b, so the coefficients are 1 and 1. So these are basically the two ones that you can see in the second row of Pascal's triangle. Now, for n equals to 2, we have a plus b squared, which we know is a squared plus 2ab plus b squared. So the coefficients are 1, 2, and 1, which you can actually see here in Pascal's triangle. We in fact, instead of determining the coefficients of Pascal's triangle, we're actually doing the expansion. Our aim is in fact the other way around, which is determining the coefficients of the expansion for higher powers of n using Pascal's triangle. So over here, what we in fact do in order to move from one row to the other one in Pascal's triangle, first of all, is that the coefficients at the ends are in fact always 1, so which you can see here at the ends of each row of Pascal's triangle we do have a 1. Then for the term in the middles, for the terms in the middle, we'd actually have each term being the sum of the two terms at the top of it. So over here, 1 plus 1 is in fact 2. 1 plus 2 is 3, and 2 plus 1 is 3. Similarly, we start with a 1, then 1 plus 3 is 4. 3 plus 3 is a 6. 3 plus 1 is a 4. Then the ends we need to put a 1. Similarly, 1 plus 4 is 5, 4 plus 6 is 10, 6 plus 4 is 10, 4 plus 1 is 5, and then at the end we have another one, etc. And that basically continues. So if I were to find the seventh row of Pascal's triangle for n equals to 6, that would in fact have 1 to start with, then 1 plus 5, that's a 6, 5 plus 10, that's a 15, 10 plus 10, that's a 20, 10 plus 5, that's another 15, and 5 plus 1, that's a 6, and then at the end we'd end with a 1. However, how could we basically use these coefficients into the terms? Now, Pascal's triangle only gives me the coefficients of the terms. But what about the rest of the factors and the terms? How are they really determined? So over here, if we go to a plus b all cubed, now going back to the cubic identities, we know that this is a cubed plus 3a squared b plus 3ab squared plus b cubed. Now, as we go from one order to the other one for n, we'd actually, by observing the terms, we'd notice that the first one always starts with the exponent. So we'd have a cubed. Similarly, here we have a squared. Similarly, here we have a to the 1. Then for the rest of the terms, the exponent of a starts decreasing by 1 until it actually gets to 0 and not be there anymore, because a to the 0 is 1. And as for b, it starts with b to the 0, and then it starts increasing until it actually reaches n in the last term. So if I were, for example, to take a plus b to the 5, now, according to Pascal's triangle, the coefficients are 1, 5, 10, 10, 5, and 1. So we'd start with a 1, then a 5, then a 10, then a 10, then a 5, then a 1. So for the first one, it's always a to the 5. So 1 times a to the 5 is a to the 5 plus. Then the exponent of a decreases by 1, it becomes a to the 4. And then it's as if we have b to the 0 here. The exponent of b increases by 1, which leaves me with a4 times b. Then, similarly, for the next one, the exponent of a decreases by 1 again, and the exponent of b increases by 1, which leaves me with a cubed b squared, plus, over here, again, that's a squared, decreasing the coefficient of a, increasing that of b by 1, leaves me with a squared, b cubed, and so on. So for the first one, it's a b to the 4 plus b to the 5 for the last one, because the exponent of a becomes 0 and a to the 0 is 1, which leaves me with b to the 5. So this is the expansion of a plus b to the 5. So over here we can see the different expansions of a plus b from an exponent of 0 all the way to the exponent of 4. However, if over here we'd have a plus b, then all the terms would have positive coefficients, would actually be having a plus for all of them. However, if we have a minus b, then the signs of the terms alternate. We start with a plus, and then we start alternating the signs as plus, minus, plus, all the way to the last one. So similarly here, if this was to be a minus b to the 5, then it would be plus, minus, plus, plus, minus. The signs would actually alternate. Okay, so however, if I needed to expand a plus b to the 20, if we go back to Pascal's triangle, in order to expand a plus b to the 20, for determining the factors of each term, that would in fact be easy. We'd follow the same pattern we've been using here. We start with a to the 20, and then we start decreasing the exponent of a by 1 and increase the exponent of b by 1 until we actually end up with b to the 20 for the last term. However, to determine the coefficients, if we were to use Pascal's triangle, we would in fact have to go to the 21st row, because in Pascal's triangle, the first row corresponds to n equals to 0. So to get to n equals to 20, we'd have to in fact cover 21 rows. And as the exponent of a plus b increases, the less practical Pascal's triangle become. So this is why we'd have to then refer to the binomial theorem. So for the binomial theorem is also used to expand factors in the form a plus b to the n. So you'd notice in the binomial expansion, the factors corresponding to a and b would in fact follow the same pattern we've been using when we determined the coefficients of the expansions using Pascal's triangle. For example, for I equals to 0, that would be a to the n, b 0. Then for I equals to 1, that would be a n minus 1, b to the 1. For I equals to 2, that would be a n minus 2, b squared, etc. So you'd notice that the exponent of a starts with n, and it decreases by 1, and the exponent of b starts with 0 and increased by 1, all the way to b to the n, all the way to reaching a to the 0, and b to the n. So that's no problem there. These factors can be determined exactly the same way as we've been doing it before. However, for the coefficients of these terms, instead of using Pascal's triangle, now the binomial theorem actually states that these coefficients are actually combinations. They're combinations where n, the exponent of the factors, in fact the total number of objects, and the number of selections depends on the rank of each row. So over here, if this one is for I equals to 0, then the coefficient would be C0 out of n. Over here, if this corresponds to I equals to 1, then in fact the coefficient would be the combination of 1 out of n. Over here, the coefficient is the combination of 2 out of n, and for the last one, the coefficient would be the combination of n out of n. So what they're saying here is that the coefficients of this expansion, which are in fact the coefficients we do find in Pascal's triangle, are in fact combinations with n as a total and I as a total number of selections. So over here, which makes a little bit of sense, because if you look at Pascal's triangle, you notice that Pascal's triangle is in fact symmetrical. And we know that the combination of p out of n is the same as the combination of n minus p out of n. So over here, if this is in fact the combination of 1 out of 4, then it would be the same as the combination of 3 out of 4. So these coefficients are in fact combinations with n as a total number of objects, and each having its rank as a number of selections. So over here, if we go back to this example, now over here we need to expand 2x plus 1 all squared using the binomial theorem. So if you were to use Pascal's triangle, you'd have to actually go 5 rows in Pascal's triangle. However, using the binomial expansion, we can immediately determine the coefficients using the corresponding combinations. So 2x plus 1 to the 4. Now over here, a is 2x, b is 1. So we need to actually start by the combination of 0 out of 4, because 4 is the exponent we're working with here. And so that's a combination of 0 out of 4 times a, which is 2x to the 4, plus combination of 1 out of 4 times. Now a decreases its exponent by 1, and b increases its exponent by 1. However, b here is 1, so all the powers of b are in fact equals to 1. So plus c2 out of 4 times a, with an exponent decreased by 1 again, so that becomes squared, plus times 1, with b having its exponent increased by 1. And that's a combination of 3 out of 4 times a, we increase the exponent again, it becomes 1, and we increase the exponent of b by 1, adding finally the combination of 4 out of 4. A has now an exponent of 0, so that's a 1, and b has an exponent of 4. However, 1 to any exponent is 1, so we're going to disregard these. Now the combination of 0 out of 4. Now we've already discussed in the previous lesson on the properties of combinations that whenever you have a combination where the total number of selections is 0 or equals to the total number of objects, in that case these combinations are in fact equals to 1. So this is 1 and this is 1. However, for the second one, C1 out of 4, whenever we have 1 as the number of selections, then the combination is in fact equal to the total number of objects. That is referring to the previous lesson on combination, the properties of combinations. And similarly, this would also be equals to 4 because 3 is in fact equal to the difference of 1 and 4, so these two combinations are equal. Well, over here, the combination of 2 out of 4 it would in fact be equals to 6. If you would look this up on your calculator, you'd in fact reach a 6 for the combination of 2 out of 4. So over here, 2 to the 4 is a 16 times 1, that's a 16x to the 4. So plus a 4 times 2 cubed, so that's 4 times 8, which is 32 x cubed. 6 times 4, that's a 24 x squared. And that's a 4 times 2, which is an 8 plus 1. So this is the expansion of 2x plus 1 to the 4. Now, going to this last example, we need to determine the constant term of this expansion. Now, over here, they're not asking for the full expansion. And usually when they don't ask for the full expansion, you do not expand the whole thing. You just look for the term they're asking for using the binomial theorem. Unlike the other example, in this example, they asked us to expand. So when they ask you to expand, you'd actually find the whole thing. Well, if they don't ask you to expand, then don't bother expanding or finding the full expansion, because sometimes the exponent could be bigger than this. Now 5 is still accessible, but however, if they did ask for the constant term of this factor to the power of 20, for example, then finding the full expansion would not really be practical, even if you were using the binomial theorem. So over here, when they ask for a specific term in the expansion, you just aim to find that term. You don't really have to expand the whole thing. So over here, x plus 2 over x to the 5, according to the binomial theorem, it's equal to the sum when I goes from 0 to 5, here since n is 5, of the combination of I out of 5 times a. A here is x. So a would actually be the total number of objects, or the exponent, minus I, times b, which is 2 over x to the power of I. So it's for a, for the first term, it would actually be 5 minus I, or n minus I, and for b, it would in fact be I, so that as you move forward in the expansion, the exponent of a decreases by 1 and the exponent of b increases by 1. Now over here, let's just rearrange this expansion a little bit. So since we have two terms in x here, so we're going to simplify them. So I'm going to leave the constants aside, so that's combination of I out of 5 times 2 to the I. That's 2 to the I here. And here we have x 5 minus I divided by x to the I. So when we divide powers of the same base, we do subtract the exponents. So that's 5 minus I, because the exponent of x here is an I. So that's x of 5 minus 2i. Now over here, if we go back to the question, they want the constant term. So the constant term is the coefficient of x to the 0. So we need to find here the exponent or the value of I that would in fact give me a constant term in this expansion. So the constant term having or being the coefficient of x to the 0, then we would consider the exponent of x and set it equals to 0. So over here, we want the constant term. Then we consider the exponent of x, which is 5 minus 2i, and set it equals to 0, which leads to I being equals to 5 over 2 or to 2.5. However, 2.5 is not a natural number because we know that I is a natural number. So 2.5 not being a natural number, it means that this expansion does not have a constant term. So we just deduce that there is no constant term in the expansion. Okay. However, if you did find a value of I, for example, here, if we want, that's part 2 if you want, this is part 1. So if we want the coefficient of x cubed. So over here, since we have already written the expansion, so the coefficient of x cubed, so we just take 5 minus 2i equals to 3. So that would in fact lead to negative 2i equals to negative 2, and that would lead me to I equals to 1. So for I equals to 1, we would end up with the coefficient of x cubed. So over here, the coefficient of x cubed would in fact be, so we consider the coefficient here of x and we replace I by 1. So the coefficient of x cubed is c1 out of 5 times 2 to the 1 times x cubed, and c1 out of 5 is a 5 times 2, that's a 10. So the term in x cubed is 10x cubed.